Okay, tonight we have to talk about inverse functions. We had a little practice with composites, so we'll start with that. The idea of an inverse function is if you took a composite, so f composite g of x. Okay, so you take the g of x, whatever answer you get for that becomes the input to f of x, right? Composite function. If you do that and you come up with back to plain old x, so what you started with is what you end up with. And it works both ways. Okay, so and you take g composite f of x. So it has to work both ways. Then we say that, f and g are inverse functions. And it's kind of interesting, and another way to think about it is that they are undoing one another. I took g of x, and then I really undid it with f of x so I could get back at the x, okay? So these two things kind of undo one another, okay? So you might think of an example where we're going to basically just guess, okay? And if I said f of x was equal to x squared, could you think of a function that would undo what f of x is doing? F of x is squaring something, and to undo that, you might guess that g of x is equal to square root of x. Okay, so that would be a really great guess. And at first glance, I would say, yeah, that's going to work. Okay, and there's one little caveat coming up. I'll have to explain something in a minute, but it gets the idea of that those two would undo each other. Okay, so let's try an example of trying to figure out two functions. I'm given an f of x is 2x plus 1, and I'm given a g of x is 1/2 times x minus 1. And the question is, are they inverses? Okay. So what you're going to do is you're going to test, does f composite g of x equal x? And then we'll do it the other way around as well. Alright, so let's test it out. Remember how we do composites. I'm going to do f of, for g of x, I'm going to make the substitution 1/2 x minus 1. Okay? So then, I have to evaluate this becomes my new x in f of x. Okay? So all of this. So that's going to equal 2 times all of this. Okay? So that was my 2x. And then I still have to do plus 1 to finish the function f. Alright, so now I'm going to evaluate this. 2 times 1/2 is just 1. I still have the x minus 1, plus 1. So you're looking at x minus 1 plus 1 is x. So indeed that worked. I took the composite and I got back to plain old x is what I started with. They undid each other. They must be inverses so far. I do have to double check that it works both ways. So let's do g of f of x. So does g of f of x equal x? Alright, so take g, and for f of x, I'm going to use this definition that it's 2x plus 1. And then I have to evaluate g using 2x plus 1 as my new x. Okay, so I have 1/2. For x, I'm going to use 2x plus 1. Okay, that's my new x. And then I have to finish it with the minus 1 here. I'll go ahead and take care of my inside the parentheses first. 2x, when I take plus 1 minus 1. And 1/2 times 2x is just x. So indeed it works. So I have proven that yes, it is an inverse function of one another. F and g are inverses. Let's take a look at this another way. Besides doing composites, one thing we can do is actually look at plotting this, graphing it. I'll start with chart of values, x versus f of x. And remember f of x was 2x plus 1. So I'll get some values, maybe 0, 1, and 2 would be easy values. So f of x would look like 2 times 0 is 0 plus 1 is 1. When x is 1, 2 times 1 is 2, plus 1 is 3. When x is 2, 2 times 2 is 4, plus 1 is 5. So there's that table of values. And then I have the other table of values when I'm doing g of x. And to show this inverse relationship, I'm going to say if I have f of x now becomes x. So I want to look at what happens when I have 1, 3, and 5 over here. So it doesn't work on a point-by-point basis is really all we're doing. And g of x, as you remember, is 1/2 x minus 1. So when I put that in there, x is 1, so 1 minus 1, 0. G of x is 0. 3 minus 1 is 2, times 1/2 is 1. And 5 minus 1 is 4, times 1/2 is 2. So you see I have these ordered pairs, 0, 1. And the inverse function is reversed 1, 0. 1, 3 in the inverse function is 3, 1. So you can say things like if a point A, B lies on f of x, then it must be true that B, A lies on the inverse function. And let me go ahead and use a notation here, f inverse of x. So I need to explain that notation. This right here is not an exponent, okay? It's not on a variable, okay? If that -1 was on a variable, I would say yes, that's an exponent. But this -1 is on a function name, the name of a function, okay? So it is not an exponent. It does not mean 1 over f of x, okay? So I just want to be really, really clear about that. When you see the f to the -1, I'm even saying it wrong. It's just read inverse function. So f to the -1 of x is read as inverse of f of x. Okay? So, you know, it's just read f inverse. Okay? Don't be doing 1 over f on me. Alright, but then we still have this nice little rule you can remember. If B lies on f of x, then A lies on f inverse of x. Okay? And I can show it to you on a graph. Let's make some x and y axes here. Okay, so I've gone ahead and I've graphed these two functions again. This time I called f inverse of x instead of g. But you had these two lines. They are inverse functions of other. And an interesting thing happens that there's some symmetry going on. These are reflections of one another, not across the x-axis like we've done before. We've done reflections across the y-axis. We've also done reflections across the origin. But this time the reflection is across a line that's not on here right now. So let me draw it in. If I drew this line right down through this middle here, and that is the line y is equal to x. Then you can see, you hold that mirror up on the line, the green line y equal x, you can see how the blue line would be a reflection of the orange line and vice versa. So that's why we have inverse functions are reflections across that line y equal x. And that'll be true for all inverse functions. So there's some really pretty graphs that can come up from this, and we'll do some of those in class. Okay, at this time it's probably important to make a note that not every function will even have an inverse, okay? Worked out in this case. And in order to have a function, okay, in order to have an inverse function, the function must be what we call a one-to-one function. What do I mean by that? Well, you remember to be a function, you got to remember the rule to be a function was for every x there was only one y, okay? So if I put an x into the f of x, I will get a certain one value out. Okay, I know which value that will be. And another way to say that was it passed the vertical line test. In order to be an inverse function, not only you put the value of x in, you get a certain value out of f of x. It also has to be true, though, that for every f of x, there's only one x. So you know which x to go back to, okay? So the idea is for every x, there's only one y, made it a function. But now we have to add for every y, there's only one x. So if you change x into y, and then you want to change y back into x, you've got to know which x to go back into. So only one x for every y. So that's why it's called one-to-one, okay? And this is summarized graphically as the horizontal line test. And let me show you how that works a little bit, because we'll do some of these for practice. Let's take, for example, that old one that we were looking at earlier when we were guessing what might be an inverse function. So that was this graph right here, y is equal to x squared. Does it have an inverse function? Well, I'm going to see, does it pass the horizontal line test? I draw a horizontal line, and I say, oops, it crosses in more than one place, okay? So the problem is when y is equal to this value, maybe it was 3 or something, the problem is I had these two different x values that give me the same y value. So that's a problem. You know, you tell me y equals 3, I don't know which x to tell you is the right answer. So this fails the horizontal line test. Okay? To pass, it crosses the graph or intersects the graph in only one place. That's how you make it a one-to-one function. Alright, so you can take a look at some other pictures and say, does it pass a horizontal line test? So one of our favorites from the past is x cubed. Does it pass the horizontal line test? You can draw all the horizontal lines you want, and you're only ever going to intersect that line, the graph, in one place. Okay, so each line only passes one time. So this is a pass. Okay, so x cubed will have an inverse function. And you might guess that it's a cubed root of 3. I'm sorry, you might guess it's a cubed root of x. Okay, the last thing left to do for us is actually to figure out how you're actually going to find the inverse when guessing isn't going to do it for us, okay? So something a little more tricky. So say f of x was x cubed minus 1. Here's the steps. There's going to be 4 steps. You memorize what these 4 steps are. You use them every time. They're not hard. You're just going to remember these 4 steps for the process. Okay, some of it's going to seem really artificial, but this is how it works. Step 1 is replace f of x with y. Okay, so that's easy. You just go out here and say y is equal to x cubed minus 1. Step 2. You actually interchange the x and y variables. So it's interchange x and y. So what you do is wherever you see a y, make it an x. Wherever you see an x, make it a y. Okay? So that's a very artificial thing. Okay? There's no algebra in here. This is just an artificial process. Step 3. You're going to solve for y. Okay, so now you're going to get to do some algebra. And let's see, I need to take the 1 over. X plus 1 is equal to y cubed. And then I need to take a cube root of both sides. So y is equal to cube root of x plus 1. And then finally, let's see if I can fit it on here. Step 4. Replace, guess what, y with f inverse of x, because you found it, okay? So step 1 and 4 are really not that hard. None of it is hard. F inverse of x is equal to cubed root x plus 1. And there you have it. I'm going to give you one to try on your own. Fun to do. And see how you do. Hold on. Okay, here's a question. Find the inverse of f of x is equal to 3x squared minus 4. Give it a try. Put it on pause. Okay, so what you should have done is you just said, oh, but Mrs. Fenker, there is no inverse. This is not a one-to-one function. And so it doesn't have one. I'm done. I would say no inverse. And that would be a great answer. You're done. But okay, fine. Let's do it. Let's fix it up so we can find an inverse, okay? So that was sort of a mean trick, but that can happen, okay? So be careful about that. Make sure it's one-to-one first. This time I'm going to say find the inverse of f of x is equal to 3x squared minus 4 when, okay, and what I have to do is restrict the domain. I can say x has to be greater than or equal to 0. Okay? When I do that, all of a sudden, remember the graph now looks like, 3x squared minus 4 is a parabola that's been moved down 4. It looks like this. It's going to be tall and skinny because of the 3. But when I said x is greater than or equal to 0, well, that's just erased all of that. Okay? So now, guess what? Because I've said x has to be greater than 0, now it does pass that horizontal line test. So indeed it will have an inverse. So let's go ahead and go through that 4-step process. You can pause it if you want, try it yourself, or just follow along. Either way is great. I'm going to do step 1 and say y is equal to 3x squared minus 4. And then I'm going to say 2, interchange the x and y. X is equal to 3y squared minus 4. Step 3 is solve for y. So I'm going to do x plus 4 is equal to 3y squared. I've got to divide by 3. So y squared is equal to x plus 4 all divided by 3. And then I still have to take a square root of both sides. The square root of x plus 4 over 3. And there's where you see, I'm taking the square root of both sides. I usually would put a plus or minus, but I don't have to now because I'm only dealing with these positive guys, okay? So, okay, let's see here. Step 4, f inverse of x is equal to the x plus 4 over 3. And I got it. Good job. I'll see you in class.